could you walk through a little bit about why maybe some of those, what some may call like higher level language concepts, are not present, when working with more constrained devices, and then how they have to be changed or adapted to be able to function in that environment? Because, kind of when reading the Virgil paper, it kind of stuck out to me that it was like, you're walking this like thin line, right, of like trying to bring in the bits of Java or Java-like language into this world, while also maintaining things like you need to be able to actually access hardware directly, right? So you can't have a runtime or something like that. What are some of those things, and how do you fit them into that environment?
Yeah, you mentioned the big one, which is the runtime system. So working on a JVM, you realize that the JVM gives your program lots of services, which is good for programs that most people write. You want to have these services, so you don't have to re-implement them yourself, like exception handling, garbage collection, like lots of libraries, right? All that takes space, and space implies like a fixed cost and also like a per class or per function or per object cost. And in a microcontroller environment, you basically cannot afford that.
Mm-hmm.
Like the base level metadata you would need for like a feature complete JVM is like far beyond a microcontroller. It's going to be like dozens or hundreds of kilobytes, if not megabytes. So for a microcontroller, if you've got a couple kilobytes or even like 256 bytes of memory, you just can't have that. So what I was going for in the virtual design is like make sure that the language doesn't imply a runtime system that has a big fixed cost. So like there's not like a lot of data structures laying around that you just need to run any code at all, like regardless of what the program is. And then also for the program, so the part of the metadata that scales with the program or is proportional to the program, keep that as minimal as possible.
Mm.
So in Java, like there's a lot of things you can do with a Java object. Like you can lock an object, you can hash an object, like it has an identity and like lots of other things too. And it's got like, lots of default methods and all that implies metadata per object. So Java object headers are probably 2 words on most VMs, and that's like a lot. Like if you imagine like you have a microcontroller and like you have an object that's got 2 integers in it, and then
Mm-hmm.
it's also got 2 header words.
Right, right.
It's like half your memory is gone just for metadata, right? So I didn't want that. So I was explicitly trying to keep that down to a minimum. So about the most that I could afford was just to have a dynamic type for an object so that you could do like casts and virtual dispatch. So virtual's object headers, at least for that, are like minimal as I could possibly make it. And there's no garbage collector because we talked about like it's initialized at compile time. And then like pretty much every other service where you go down the line and you look at it, like what would you need to implement it? It's like just don't have that.
Right, right. And you mentioned kind of like three key optimizations. I think they were even mentioned in maybe the abstract for the paper. One that's kind of relevant to what you're talking about, and maybe we could step through each of them. Is reference compression, where you're kind of like talking about the difference between a C pointer and a Java reference or something like that. And you're talking about the metadata encapsulated in it, because you're when you bring type safety into a program, you have to understand what you're referencing, right, when you're pointing to something. Can you talk about how Virgil handled that, and maybe how that kind of like struck the balance?
Yeah, it might be going a little bit too deep on the old Virgil, so to speak, the microcontroller Virgil. But that work was basically like since you have a fixed number of objects, you know how many there are. You can't allocate any more. The idea is basically, well, instead of having a pointer to an object, you just have an indirection, and so you just have a table.
Mm-hmm.
And so you can use a fewer number of bits to represent a reference because it's just an index into a table. Typical trick, right? It's like another layer of indirection. It's like the one weird trick that CS people use.
Right.
So that means that like, if you only have 15 objects and null to represent, you only need 4 bits.
Mm-hmm.
And so then you can bit pack a field. And so wherever they go, like it just takes less space. And that turned out to be a pretty big win. One of the things that made that even better is that Virgil doesn't have like a class that's the superclass of all classes. So there's no like object at the top. And that means that separate class hierarchies cannot possibly ever be aliases. Like you can't have a reference that points to this hierarchy or that hierarchy. It can only be one. And so you can compress the references separately, just based on a type-based analysis as opposed to doing some pointer analysis. I mean, advanced pointer analysis might be able to figure that out even with the presence of object, but I liked type-based analysis. It was easier to do it that way.
Hmm.
And so it's like very easy to understand, like, oh, this hierarchy is like only these four objects that ever exist. So that worked out pretty well. Another optimization was like some parts of objects are often immutable. So if you split the object in half, and again, because you have an indirection, it's not a pointer to memory, it's a number. You can put the read-only part in ROM,
Mm.
and then you put the read-write part in RAM. And so that saves a bunch of memory too.
Absolutely. Yeah, I was not familiar with the term romization, which I think is what that was referred to in the
Yeah,
paper. But I like it. I think it's pretty descriptive of what you're doing there.
yeah.
The other optimization that you mentioned, and then maybe we can jump on to some of the things you worked on after grad school, was reachable members analysis. Can you talk a little bit about how that worked?
Yeah, this is actually the most important optimization. So that if you think about it, like dead code elimination and like linker deduplication are really just scratching the surface of what a compiler can do for optimizing away dead code. What reachable members does is basically imagine that you don't have any code in your program at all. And what code do you need? Well, obviously you need the main function. So if you bring in the main function and then you analyze statically what the main calls or what it uses, then you have to bring in those.
Hmm.
So reachability, that's why it's in the name. It's like obviously the things that main uses and then transitively what those things use. So reachable members analysis basically brings in both the code and the data, which is reachable from main. So if you have like a big library that has a bunch of stuff in it, but you don't actually use that, only the stuff that your program actually does use that is determined by the compiler by starting from main. It's a naturally and necessarily a whole program optimization. You need to have all of the code in order to be able to analyze it. For microcontrollers, that's not a big deal because it may be only a few thousand files or lines or whatever. So you just have it all in memory and you just do this analysis.
Hmm.
And it not only is for code, but also for data. So like imagine you have an object, but like in the reachable code, you never actually refer to some field of this object. Well, then it can't ever influence the program execution. So you can just remove it. And obviously everything that it references. So I call it reachable members analysis. Other people might call it dead code elimination, but I like think of it in terms of reachability because the dead stuff it actually never sees. And so
Hmm.
even in the cost of analysis is only the things that are reachable that the compiler spends any time or space on.
Gotcha. Yeah, you could almost think of it. Well, correct me if this is wrong, but the way you just explained it, it's almost like you're looking more at instead of trying to look for what doesn't get touched, you're only looking at what does get touched,
Exactly, yeah.
which could obviously be more efficient in some cases as well if there's a large discrepancy between those two things.
Yeah. So in the current version of Virgil, like I took that idea even further, like it does devirtualization based on reachable members analysis. It will do inferring constants for fields. So like imagine your program, it allocates objects, but this one field is like a configuration and it only ever points to objects of a certain type, or it only points to an object, a specific object, or maybe it's only 42. The compiler, as part of that reachable members analysis, will figure out that it's actually a constant, remove the whole thing, and smash the constant in. So it will do specialization, basically, to the data that is present from your initialization. And it turns out to like kick in so many things, like because so many optimizations follow from constant propagation. So like imagine like this, you figure out this field is always null. And like
Hmm.
there's checks all over the place. Is this thing null? Well, you know which way they go. And so like a bunch of code like folds away too.